Welcome to MA320 Linear Algebra. This will be your first lesson in linear algebra, and it begins with section 1.1, Systems of Linear Equations. We will find that systems of equations are the heart of linear algebra. This chapter introduces some of the central concepts of this subject. In fact, sections 1.1 and 1.2 are the building blocks that will be used throughout the entire course. So it's very important that you feel comfortable with the first two sections. To begin with, we'll talk about the definition of a linear equation. And it's something that you should be very familiar with. It's nothing out of the ordinary, but the notation might be a little bit new. So for the variables, we will have a subscript next to the x. And in class, this n, this subscript, is typically going to be 2 to 5. So there will be about, at most, 5 terms in each of these linear equations. But in the real world, and that's what this course is trying to prepare you for, there could be tons of terms in this equation, 5,000 plus. Okay, so we'll just kind of get started slowly once we get into some examples. Recall, a solution of a system of linear equations is all of the values that make the equation true. And the nice thing about these problems is that you can check every single answer that you come up with. Two linear systems are considered equivalent if they have the same solution set. You may also remember when dealing with systems that there can either be no solution, exactly one solution, or many solutions. And we will experience all of these cases. If a system of linear equations has at least one solution, we refer to it as being consistent. Otherwise, if there are no solutions, we say that it is inconsistent. Graphically speaking, there are different ways to represent each of these three situations. You may recall from previous math classes that a system of equations has no solution if you have parallel lines. These lines will never intersect, so they will not have a solution for that system. An example of a system with no solution would be x1 minus 2x2 is equal to -1, and negative x1 plus 2x2 is equal to 3. If you solve this, you'll find that you get 0 on the left-hand side is equal to 2, which is a false statement. Exactly one solution will occur when the lines intersect in one location. An example of this system would be x1 minus 2x2 is equal to -1. Negative x1 plus 3x2 is equal to 3. Finally, infinitely many solutions will look like one line and another line directly on top of it. Because there are an infinitely many number of intersections, there are infinitely many solutions. This would have an equation, a system of equations like x1 minus 2x2 is equal to -1, and negative x1 plus 2x2 is equal to 1. Now, in your previous math classes, when you would solve these systems of equations, you would use substitution, elimination, graphing, maybe some other different methods. But in this class, the primary means of solving systems is through matrices. So you may recall from your other math classes that a matrix looks like these. And what we'll do is we'll take a system, and so an example like this, and we will basically remove all the fancy notation and just keep the coefficients. So what we'll do is we'll take the coefficients here and place them here. This is called the coefficient matrix. The augmented matrix over here contains the coefficient matrix with the added column of the constants from the right-hand side of the equation. So this is referred to as the augmented matrix. The size of a matrix is often referred to as M by N, and this tells us how many rows and columns there are. When we give the dimensions of a matrix, it is always the number of rows by the number of columns. Every time, RC. Okay. Matrices will help us solve. And when we are doing this, there are three primary row operations that we will use, and they are stated here. Replacement, interchange, and scaling. And these are new. It's something that is very unique. But once you get the hang of it, I think you'll actually find it enjoyable. So to solve a system of equations, we will use these three row operations in order to solve. So replacement basically replaces one row by some multiple of another row in itself. So basically we might add row 1 to a multiple of another row, and that will replace that row. Interchange just means flip-flopping two rows, and then scaling just means multiplying an entire row by a specific number. So what you're going to be doing is you are going to be trying to create zeros and ones in several entries. And it's called a triangular form. And I want you to keep a very open mind as I go through this first example, because it is different, it is strange, but I think once you get into it, Here is our first example, and I want to urge you to keep an open mind as I'm going through this. I'll do several examples today so that you can get the hang of what's going on. The first thing we want to do is we want to rewrite this system of equations as an augmented matrix. Oh, and I'm sorry, this should be a 1. So when we do this, this system of equations becomes 0, 1, 2, 8, 1, 1, negative 1, 0, 1, negative 3, 2, and 1. So this is the augmented matrix of that system of equations. Now, when you are working in this class, you'll be dealing with matrices very often. I encourage you to check and double check your work, because if you have one incorrect entry, you will probably be a little upset. Okay. Now, what we want to do is we want to change this, this matrix so that it is something that is easier for us to solve. And the way we do that is we try to have these entries be zeros and ones only. And it takes a lot of manipulating in order to achieve that. Okay, so that's when we use those three different operations. Another thing is this entry here can never be 0. The goal is to get that entry to be a 1. So the first thing we want to do is we want to interchange two rows, because what I can do is I can take the second row and switch it with the first row, and then I will have achieved that goal. So the way I'm going to illustrate that is I'm going to take row 1, switch it with row 2, and this is called interchange. So of those three operations, this is interchange. So my matrix will become 1, 1, negative 1, 0, 0, 1, 2, 8. And then the third row remains the same, 1, negative 3, 2, and 1. And now we have 1 in that first entry, which makes us happy. Now, the next thing we want to do is we want everything below this 1, we want everything below that to be 0. So in that column, everything should be 0. So what I'm going to do is I need to try to make this 0. And the way I will do that, and there are different ways you can do this, but what I'm going to do is I'm going to take row 1 and I'm going to multiply it by a negative 1, and then I'm going to add that to row 3. This is referred to as replacement. And this operation that I'm going to do is going to become the new row 3. So when I rewrite this matrix, the first two rows stay the same, but the third row is going to be replaced with something different. So the first thing I want to do is I want to take row 1 and multiply it by negative 1. So when I do that, this becomes negative 1, 1, and 0. And I'm going to add that to row 3, and that will become my new entry. So I'll have negative 1 plus 1, which is 0. Negative 1 plus negative 3 is negative 4. 1 plus 2 is 3, and 0 plus 1 is 1. So I have this new matrix. Okay, well, I'm going to keep trucking along. Now, it is good that this is a 1 and this is a 1. It is also good that these are zeros. What I'm going to do now is I'm going to try to make this a 0. And I can use either row 1 or row 2 to do that. It's up to me, but I might want to choose something with a 0 in it, because then it's a little bit easier. So what I'm going to do is I'm going to take row 2 and multiply it by 4, because if I multiply this entry by 4 and add it to row 3, then this term will become 0. This again is called replacement, and this will become the new row 3. Now, I know this is different and confusing, but just hang tight and just keep trucking along with me. So the only row that's changing is row 3. So I'm going to just rewrite row 1 and row 2. And row 3 is going to be found by using this set of operations here. So I'm going to take row 2 and multiply everything by 4. So when I do that, I get 0, 4, 8, and 32. Okay, then I'm going to add that to row 3. 0 plus 0 is 0. 4 plus negative 4 is 0. 8 plus 3 is 11. And 32 plus 1 is 33. Okay, we are getting closer to our goal. Now, we want to have ones at the diagonal. I have one here, I have one here. I want to make this a 1. And the way I'm going to do that is by scaling. And all I'm going to do is I'm going to take row 3 and divide it by 11, or 1/11 times row 3. This is an example of scaling. And this will become my new row 3. So rows 1 and 2 stay the same. But row 3, I divide everything by 11. So I have 0, 0, 1, and 3. This is a system of triangular form. And the reason it's triangular form is because I have zeros down here and ones at the diagonal. This makes us very, very happy. Okay, now unfortunately we're not quite done with this problem, but once you get here you're really home free. And what we want to do now is we want all of these entries here to become 0. Okay, so if we can achieve that, then our answer to this system of equations will be more straightforward. In order to achieve this, it's typically easiest to start from the right and work your way to the left. So that's often what I'll do, unless there's something a little bit easier to make that happen. Now, looking at this, I notice that if I add row 1, let's see, if I multiply row 2 by a -1, then I can add it to row 1 and that will become 0, which would be great. In the order in which you do this, it doesn't really matter as long as you end up at the correct answer. So I'm going to take -1 times row 2 and add it to row 1. This is replacement. And this will become the new row 1. So you might notice that whatever this is what changes. Okay, so let's write this new matrix. So I'm going to multiply row 2 by -1 and add it to row 1. So the only row that's going to be changing is row 1. We'll have 1, 0, -3, and -8. Rows 2 and 3 remain the same. Okay, we're getting closer. Now what I'm going to do is I'm going to try to make this 0. Now looking at this, I notice that this is a 1, which is probably a lot easier to work with, because if I multiply row 3 by 3 and add it to row 1, boom, I'm good to go. So I'm going to multiply row 3 by 3 and add it to row 1. This is replacement. And I will have a new row 1. So when I multiply row 3 by 3. I get 0, 0, 3, and 9. I'm going to add that to row 1 to get 1, 0, 0, and 1. Rows 2 and 3 remain the same. All right, we have only one more entry, which is this one here. I want that to be 0. If I multiply row 3 by -2 and add it, then I'm in good shape. So I'm going to multiply row 3 by -2 and add it to row 2. This is replacement. And this will become my new row 2. All right, let's do it. So row 1 remains the same. Row 2 becomes 0, 1, 0, 2. And row 3 stays the same. We will talk about this form more in the next section, but this is referred to as reduced row echelon form. And what that means is we have 1s here, 0s here, 0s here. And this helps us identify what the solution is. When we set up our matrix, this first column represented x1, the second column represented x2, and the third column represented x3. And these are the constants. So what this tells us, wherever the 1 is, represents the variable. So x1 is equal to 1. x2 is equal to 2. And x3 is equal to 3. I can write this in parentheses as 1, 2, 3. This is the solution to this system of equations. Remember, you can check your answers by plugging each of these values in, and it must work in all 3 equations. So just quickly plug them in, verify that they work, and if so, you are good to go. Now, I know that that was a lot to take in. So let's do another example and try to achieve the same thing. All right, the first thing we want to do is set up our augmented matrix. That's the easy step. Remember, when you are writing this, check and double check that you have all of the entries copied correctly. It is so easy to make such tiny, tiny mistakes here, and they will add up. Okay, so here's my augmented matrix. I'd like to emphasize that this first entry is 1, which makes us happy. That's always the great place to check. Since that's 1, we can move on and try to figure something else out. Now, looking at this, I want to remind you that everything below that 1 needs to be a 0. So what I'm going to do first is I'm going to work with this here. I want that to become 0. Now, there's nothing I can really do with row 2 to achieve that goal, but I can multiply row 1 by 4 and add it to row 3. So I'm going to multiply row 1 by 4 and add it to row 3. And this will become my new row 3. So everything else will stay the same. I will simply copy over row 1 and row 2. and then row 3 changes. So I'm going to multiply the first row by 4. So this will become 4, -8, 4, and 0. And I'm going to add that to row 3. 4 plus -4 is 0. -8 plus 5 is -3. 4 plus 9 is 13. And 0 plus 9 is, oh, typo. This should be a -9. I hope you caught that. 0 plus -9 is -9. See how easy it is to make mistakes? Okay, off to a great start. Now I have this column the way I like it. So now let's move over to the next column. I want this to be a 1. In order to do that, all I need to do is divide by 2, and then that becomes a 1. So this is scalar. I'm going to scale, and I'm going to multiply row 2 by 1/2, which is the same thing as dividing by 2. And this will become my new row 2. So everything else will stay the same. So my first row is 1, -2, 1, 0. The second row, I'm going to divide everything by 2. So I have 0, 1, -4, and 4. And then row 3 will remain the same. Okay, now I want this to be a 0. Now looking at this, the easiest thing to do is use these two rows. Because if I take row 2 and multiply it by a 3, this will be a 3. I add the 2 together, boom, I'm happy. So I'm going to take 3 times row 2 and add it to row 3. This will become my new row 3. Okay, so row 1 stays the same, and so does row 2. Row 3 becomes 0, 0, 1, 3. Excellent. Okay, we are doing so well. We have our triangular form. I'm sorry, what happened here? This should just be a 1. Sorry. Okay, so I need to make these zeros. And you can go about doing that however you want. So the first thing I'll change this one here. And it looks like I can choose to multiply either row 1 or row 3 by 4. Now, I would recommend using row 3. I would use these two rows because row 3 has some zeros and it's going to be a lot easier to manage those. So I'm going to take row 3 and multiply it by 4, and then I'm going to add it to row 2. And this will become the new row 2. Okay, so we have 1, -2, 1, 0. Row 2 will become 0, 1, 0, 16. Row 3 stays as is. All right, now I'm going to try to change this. I'm going to use these two rows. I'm going to multiply row 2 by a +2 and add it to row 1. This will give me a new row 1. When I multiply row 2 by 2, I have 0 plus 1, which is 1. 2 plus a negative 2 is 0. 0 plus 1 is 1. This is 32 plus 0 is 32. In row 2 and 3 are the same. We are oh so close. Last thing we need to do is eliminate this. Looking at this, it appears that row 1 and 3 are the ones I want to manipulate. I'm going to multiply row 3 by negative 1 and add that to row 1 because I need the row 1 to change. So this last operation gives us 1, 0, 0, 29, 0, 1, 0, 16, 0, 0, 1, 3. This is in reduced row echelon form. This represents the answer for x1. So the solution is x1 equals 29. x2 is 16. And x3 is 3. I can write this as an ordered pair, 29, 16, 3. So this is the solution to this system of equations. Remember, you can check this by plugging 29 in anywhere you see x1, plug in 16 anywhere you see x2, and plug in 3 anywhere you see x3. If all three of these equations work out, you are in good shape. Okay. So, so just a little bit more about this. So as far as row operations are concerned, two matrices are called row equivalent if there is a sequence of row operations that makes one matrix into the other. Row operations are reversible, and if two augmented matrices of two linear systems are row equivalent, then they are considered to have the same solution set. The questions that we want to answer is the system consistent? So does the system have at least one solution? And if a solution exists, is there only one solution or many solutions? And these questions are going to really be answered in the next section. There are a little bit more that I want, there's a couple more examples I want to show you. I want to kind of lead us into the next section a little bit. So I'm going to show you what happens if we end up with no solution. Okay, so here is our system of equations. We are going to attempt to solve this using our row operations the same way we've done previously. So let's do it. Let's set up our augmented matrix. If there isn't a term, make sure you put a 0 in the matrix to hold that place. Make sure you write down your augmented matrix correctly. As illustrated previously, it is easy to make tiny mistakes. Okay, here is our augmented matrix. Now, I want to show you something that's happening here. In our first entry, you may notice that it is not 1. When that's not 1, typically what we do is we interchange two rows. But no matter which one I choose, if I choose row 2 or row 3, it is still not a 1. So there's a little bit more that we're going to have to do. But we are smart, so it's no problem. Pick one of the two rows to interchange. It doesn't matter. I'll interchange 1 and 2. So just recall this is referred to as interchanging. So I'm just going to flip-flop those two rows. So my first row becomes 2, -3, 2, 1. Second row is 0, 1, -4, and 8. And the third row remains the same. Oops. Okay. Now, I'm going to get to that first entry in a little bit. The first thing I want to do is get rid of this. I want that to become a 0. And the way I'm going to do that, the only way I can make that a 0 is if I get some fractions involved, which is fine, don't freak out. What I'm going to do is I'm going to multiply row 1 by -5/2. Because 2 times -5/2 is -5, and then if I add that to row 3, this becomes a 0 as desired. So -5/2 times row 1 plus row 3 will produce a new row 3. So this matrix becomes rows 1 and 2 remain the same. But row 3 becomes 0, -1/2, 2, and -3/2. Okay, now I want, let's see here. So this is a 1, that's great. I want to make this a 0. Because if I make that a 0, then I have my almost my triangular form, and then I just need to work on these becoming 1. Okay, so I'm going to work on this right here. I need to find a way to make that 0. And what I'm going to do is I'm going to use row 2 and 3. I'm going to multiply row 2 by 1/2, because 1/2 plus a -1/2, boom, it goes away. So 1/2 times row 2, add it to row 3. This will become my new row 3. Now, I know that there are calculator tools and things online that will solve these matrices for you. I'm telling you now that this is the work that I want to see on any assessment you have. Do not get in the habit of doing these matrices on some other device, because you will not receive full credit on an assessment. If you want to use those to check your work, that's perfectly acceptable. Okay, but I want you to do this by hand for now. Okay, so here comes our new matrix. 2, -3, 2, 1. 0, 1, -4, 8, 0, 0, 0, 5/2. Huh. Oh my gosh, this is something we haven't seen yet. Hopefully you are noticing that this last row has something goofy going on. You'll notice that all of these entries are 0. If I write this in equation, like if I write this as a linear equation, it would be 0x1 plus 0x2, because remember these represent the coefficients, plus 0x3 is equal to 5/2. Well, 0 times anything is 0. And last time I checked, 0 does not equal 5/2. This is never true. This is a problem. Uh-oh. This means that this is an inconsistent system of equations. And remember, an inconsistent system of equations means that there is no solution. So if you run into something that looks like this, you will be prepared. This is the last type of problem I want to show you. And this one's a little bit different because now we have some variables involved. And I want to know for which values of h and K will make this system consistent. Okay, so that means I do not want no solution. Okay, all right, well, let's go ahead and set this up. When I set this up, I will set it up the exact same way as we've done previously. I will also solve this the same way as I've done previously. Now, looking at this, I know that this should be 1, but that's not my primary issue. What I'm going to try to do is make this 0. Okay, so then I'll come back to that first entry. So what I'm going to do is try to find a way to manipulate row 1 and add it to row 2 to get to make that a 0. And the way I do that is I take 3 times row 1, add it to row 2, and that will become my new row 2. So row 1 is the exact same thing, but row 2 becomes 0, 0, 3H, because I'm multiplying this by 3, plus K. So that last entry is just all of this, which is perfectly fine. Okay, now, if you look at this, this second row resembles something very similar to what we saw in the previous example. Now, we do not want this to be something other than 0. Okay, because if 3H plus K is not equal to 0, then it will be inconsistent. Inconsistent. Because if this is not 0, then we'll have 0 equals 7, 0 equals -3. So if this is not 0, it's inconsistent. So in order for this to be a consistent system, we want 3H plus K to equal 0. So it will be consistent for any values of H and K that make 3H plus K equal 0. You will run into some examples in your homework similar to this. This concludes your lesson for section 1.1. Good luck on your homework.